All right, so in this module, we are going to be going over the basic foundations for generalized causal inference or experiments. We're going to start with foundations of statistics, and then we're going to move into the ideas for reliability and validity in the experiment, and then we'll end with formulating precise research questions. So foundations. We already did that. Inference is a conclusion reached on the basis of evidence and reasoning. So when we talk about a general causal inference, we are reaching a conclusion on the basis of evidence and reasoning. So we have two ideas here. We have the population, which is the whole group of people that we're looking at. And this doesn't mean everybody in a population. This could mean the population of a school. This could mean the population of a school district. This could mean the population of a state, the United States in general, and it could get bigger from that. But, or we could be looking at fourth graders, or we could be looking at fifth graders. So population doesn't mean everybody. It just means everybody that we are expecting to transfer the results of our study to meet this population. So our sample is a few people from this population. So this is a few fourth graders from a bigger pool of fourth graders. We have abstract versus tangible populations. Tangible means we have the ability to think about or distinguish each person in the population. For example, I poll people in spring 2016 and draw conclusions about what's going to happen in spring of 2016. In the abstract, the people we are talking about are not from the original population. For example, I poll people in spring 2016 to make inferences about those people in the fall of 2018. We use descriptive statistics to report on populations and samples. These are summary descriptions of measurements, like variables, taken about a group of people. We do this by summarizing information. Descriptive statistics speed up and simplify comprehension of a group's characteristics. So an illustration of this, which group is smarter? So we have all these people over here in class A, and we have their IQ scores. And we have the IQ scores of those people in class B. Well, it's kind of hard to make a assumption about who's smarter or what based on this, because we don't have any sort of averaging of the scores. All we see are these scores, and it's hard to tell between the two. But now we can see Class A's average was 110.54 and Class B's average was 110.23, and they're roughly the same. So we used a average to look at these scores and make a determination about whether or not they're the same or not. So we can do different types of things when we're looking at descriptive statistics. We can do tables, frequency distributions, relative frequency distributions, and then we'll be talking a lot about skewness and kurtosis, particularly when we get farther along into the statistical parts of this. And we can use graphs, bar charts, or histograms, stem and leaf plots, or frequency polygons. Generally speaking, when we put descriptive statistics in a manuscript, we're going to be using tables and not graphs. I haven't seen a graph of descriptive statistics in the whole time that I've been working. So just know that this is probably going to end up in a table, not in a graph form. So if we pop this stuff out in SPSS, we have all these IQs down here, and we have the frequency of getting each of these IQs here, the percent of people that have the frequency, and then the cumulative percent, meaning that 4.2% was here, and then we added, and then we added, and then we added, and it ends up to 100. We can also look at a histogram, and histograms are going to be useful, especially when we're looking for violations of normality and those types of things. So the histogram is saying that most of the people are right around the 100, maybe just shy of it, and then we see it trail off over here. And in an IQ score, we would expect the average to always be around 100, because an average IQ is 100. Then we have a bar graph of the number of students in two classes, and we see that not much has changed. So that didn't tell us a whole lot. And then we have a stem and leaf plot, and the way that this works is that we have 82, 87, 89. We have 93, 96, 97, 98. We have 102, 103, and so on. And so this just gives us kind of another way to look at this. So when we do descriptive statistics, we usually summarize the data, generally speaking, with some measure of central tendency. Generally speaking, the mean is the most used, but sometimes we'll use the median. It just kind of depends on what we're looking at. But in broad terms, when we're talking about listing the average score of a group of people, we use the mean. And in variation, the general one that we end up using is the standard deviation, though there is also the variance, the interquartile range, and the range. And sometimes it's necessary to use the range. It's sometimes necessary to use all these. But generally, when we're looking at, I'm just going to present the results of IQ scores for this class, we would use the mean and the standard deviation. The mean is most commonly called the average. It's the adding up the values for each case and dividing by the total number of cases. And here's the formula for doing that, but we're not going to spend too much time on the formulas. So the mean of these students is the sum of yi equals 1437, blah, 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 gives us 110.54 and 110.23. And the statistical packages that we're going to use are going to add all this stuff up for you, so we don't need to worry about that too much. Means, though, can be affected by outliers, which means data points with extreme values unlike the rest. So outliers can make the mean a bad measure of central tendency or common experience if we're talking about the mean income in the United States. So as you can see, the mean really goes up here, but then we have people like Bill Gates and Warren Buffett who throw that whole thing off. And so it actually makes the mean move into a place where we wouldn't expect necessarily the average score to be. In that case, we might want to use the median, which is the middle value when a variable's values are ranked in order, the point that divides a distribution into two equal halves. When data are listed in order, the median is the point at which 50% of the cases are above and 50 below it. It's also called the 50th percentile. So when we take this group of numbers here, 89, 93, 97, we're going to count up how many are. There's 6 cases above and 6 cases below. The median then is 109. If we get rid of one of those, the median equals 109.5, because 109 and 110, we had to draw a line here to get in between the middle. We then needed to be able to figure out the difference between 109 and 110 equals 219 divided by 2, because we had 2 here. So when we're working with odd numbers, it's really easy because you just pick the one in the middle. When we're working with even numbers, we have to take the 2 in the middle and divide them. The median is unaffected by outliers, making it a better measure of central tendency, better describing the typical person than the mean when data are skewed. So we don't really have any issue with Bill Gates or Warren Buffett making a whole lot of money, because the median is going to be the middle score. If the recorded values for a variable from a symmetric distribution, the median and the mean are identical. So if it's symmetrical, if it's going up like this and going down like this, and it looks even on both sides, the mean and the median are going to be the same. However, when it's skewed, the median is going to reflect a more, agreeable measure than the mean would, because the mean is being taken over by these outliers. The middle scores are the measurement in a set of ranked scores or measurements, the point that divides the distribution into 2 equal halves. Data are listed in order. We already talked about that, but let's just go ahead and delete that now. The mode is the most common data point in a distribution. So the combined IQ scores for classes A and B, we had 2, 3, 109s. And so the mode then is 109. It is also possible, though, to have more than one mode, as we can see here. So we would call this bimodal, where we had a couple of 80-somethings and then a couple of 120-somethings, and so we had 2 modes within this distribution. It may give you the most likely experience rather than the typical or central experience. In symmetric distributions, the mean, median, and mode are the same. So in a symmetric distribution, we're seeing that the mode happened the most frequently right in here, just like the mean and the median. And then in skewed data, the mean and median lie further toward the skew than the mode does. So the mode is going to probably be right here at this peak. Skewness is what we're talking about when we're looking at, if we see a normal distribution like this, skewness means that it is tailed off to one end or the other. It's a measure of the asymmetry of the probability distribution of a real valued random variable about its mean. So a negative skew means it's tailing to the right, and positive skew means it's tailing to the left. Kurtosis is a measure of the peakedness of the probability distribution of a real valued random variable. We look at the shape of the peak. A high kurtosis distribution has a sharper peak and fatter tails, while a low kurtosis distribution has a more rounded peak and thinner tails. So what's too much? We can use the citation by George and Mallory that says that for both, -2 and +2 are considered acceptable in order to prove normal univariate distribution. So we will, through various statistical measures, when we get a little bit further down the road, we will be able to determine the skewness and the kurtosis of this. So the skewness is whether or not it's leaning to the left or the right, and the kurtosis is how up it goes or how flat it is. Then we have the range. I think that's where I am. Oh, why do we care? Most statistical tests, like t-tests and ANOVA, assume normality. Skewed and kurtotic data violate these assumptions, so we need to make sure that we're within that framework of -2 or +2 in order to be able to say that we meet the assumptions of t-test or ANOVA, and then we can move on. So now let's talk about the range. It's the spread or the distance between the lowest and highest values of a variable. To get the range of a variable, you subtract its lowest value from its highest value. So we have 140 being the highest and 89, so our range is 51. Class B, our range is 82. So we see a little bit more distribution in Class B than we saw in Class A. The interquartile range is the quartile is the value that marks one of the divisions that breaks a series of values into 4 equal parts. The median is a quartile and divides the cases in half. The 25th percentile is then divided that into half, and then the 75th percentile is dividing the upper portion in half. The interquartile range is the distance or range between the 25th percentile and the 75th percentile. Below is what is the interquartile range. So what is the range from here to here? Is essentially what that's asking. The variance is a measure of the spread of the recorded variables values on a variable, and it's a measure of dispersion, so it's measuring how spread out this thing is, just like the range does. The larger the variance, the further the individual cases are from the mean. The smaller the variance, the closer the individual scores are to the mean. So this is giving us kind of an idea of it gets used in the confidence interval. So if we're clustered really close here to the mean, we're going to have a smaller variance. If we have scores that are spread out all along here, then we're going to have a larger variance. Variance is a number that at first seems complex. Calculating variance starts with a deviation. A deviation is the distance away from the mean of a case's score. If the average person's car costs $20,000, my deviation from the mean is minus $14,000. So 6K minus 20K equals negative 14K. For Class A, the variance was 282.5.39 divided by n minus 1, blah, 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 blah. How helpful is that in reality? That's why we generally don't report the variance on statistical, when we're providing descriptive statistics. We don't usually talk about the variance as much as we'll talk about the standard deviation. And the standard deviation is converting that variance into something that actually has meaning. So the square root of the variance reveals the average deviation of the observations from the mean. That's weird. So the standard deviation allows us to say, okay, well, if, let's go back to here. So if my mean goes right down here, a standard deviation of 1 would put us right down here, and a standard deviation of 2 would put us right here. So it gives us an idea of how far away are we from the mean, and so how likely is it that we are going to find something in this area here. And so it just gives us a standardized measure. So if we're one standard deviation above the mean, we can kind of say, well, they're doing pretty good. If we're one standard deviation below the mean, we can say, well, we're doing kind of bad. And the way that we look at it in a grading scale, the mean would be a C. This would be the B's. And then the A's would fall in here. And then we would have D and F, which is why this grading scale was developed in the way that it was, because we were given an opportunity to say, well, the B's were doing a lot better than the average, the D's were doing less well than the average, and the F's were, you know, we shouldn't have too many of them, but they were doing 2 standard deviations below the mean. Okay. So then we move to correlational designs just as a kind of refresh. It examines the relationship or association between 2 or more variables. It is useful in predicting an outcome. We can look at how variables covary together, and by covary we mean that as one moves, the other one moves. And we use one variable to predict the score on another variable. Characteristics of correlational designs: we can displays of scores, scatter plots, and matrices. We can look at the association between scores, and we look at multiple variable analysis, partial correlations, and multiple regression. So if we look at the scores of the hours of internet use per week and scores on a depression inventory, we see that there is a correlation or an association between the hours of internet use here and their score on that depression inventory. So we're assuming that a higher score on the depression inventory means that they're more depressed. And so as you use internet more often, we're seeing an upward trend. So we can say that there is an association. We don't know that it's the cause, but we can see that there is an association between these 2 scores and this going up. So in a correlation matrix, what you're going to find is that you're going to say school satisfaction, extracurricular activities. So these are on some sort of a survey of school engagement, I'm guessing. But what we're seeing here is we see this 1 here, and this 1 is the same as this 1. And so they're going to be perfectly correlated. So we usually have a dash there that shows that these 2 are perfectly correlated. And so then this is how much association is there between school satisfaction and extracurricular activities, and then how much is there between school satisfaction and friendship, and then school satisfaction and self-esteem. And we can see that extracurricular activities are associated with school satisfaction, as is self-awareness. And then we look at the correlation matrix across here, and this would be extracurricular activities, and we see that self-esteem and extracurricular activities are highly associated with each other. And then this would be friendship and self-esteem, friendship and pride in school, friendship and self-awareness. So that's kind of how you read those matrices. A lot of times we'll get a printout that will have numbers up here, but for publication purposes and our purposes, we would delete those because they're redundant, because this 0.33 would end up being right there, because 1 and 2 are associated and 1 and 2 are associated. So we look at the direction. Is it positive or negative? We look at the form. Is it linear or nonlinear? And we look at the degree and strength of the coefficient. And that coefficient is R. So a positive linear trend looks like this. So it's going from 0 down here and upwards. A negative linear trend means that we're starting with high scores and we're getting lower as we go away. And no correlation is just going to be all of them kind of bumbled up in the center. We also have curvilinear trends, also called sometimes quadratic trends, because what they're doing is they're not following in a straight line, they're moving and then moving again. And there's different forms for that. So as a general rule of thumb, when we're looking at the R, so this is interpreting R, 0.2 to 0.35, there's only a slight relationship. 0.3 to 0.56 are useful for limited prediction. 0.6 to 0.85, correlations fall into this range, they're pretty good. And and 0.86 and above is going to be very good. And usually when we're looking at test-retest reliability or reliability in general, we're looking at something above 0.8. But these things are going to be dependent on sample size, and so this is a rule of thumb, but this isn't to mean that we should take, you know, the idea of statistical significance by this, because the software will tell us whether or not we have a strong prediction at the 0.05 level or whatever of this correlation being significant. So a simple regression line, we can look back to this correlation matrix, and the simple regression line is coming right up here. And so the regression, the intercept is here. We have dispersion scores going up here, hours of internet use here, and we have our regression line going up, and the slope is how much gain we make for each increase in one. So that should give us kind of a refresher on all these things. These things shouldn't be new concepts. We should have learned them in 816 and 817 or in undergraduate stats classes or in high school stats classes or somewhere. These should all be, generally speaking, refreshers. If you're feeling like they're not refreshers, either we skipped something and you should be in the class, although don't go dropping, and or it's been a long time and we've forgotten it, which is fine, but I would recommend that you kind of go back over this and look through the materials, and if you're still having a hard time with something, maybe look up Google and look up, you know, the meaning of variance and figure it out that way, or how one thing is different than the other. So for right now, we're going to move on to the validity of inference. There was this horse, and this horse was able to, it was Clever Hans, and he was able to solve math problems. I think it was math problems. And essentially what would end up happening is this guy would take this horse around and he would just amaze everybody about how clever this horse was. Well, then there was an observer in the audience that was a little bit skeptical, maybe a little bit like me, and he said, well, I'm watching this and it's pretty amazing, but then I started watching the horse, and the horse isn't really looking here, he's looking here, and he's reading cues from Willem van Osten. And by reading those cues, whether or not he was doing it on purpose or not is, you know, I'm not debating that part of it, but what we are able to see is if you remove Willem van Osten from the equation, Clever Hans can no longer do math problems. And so this comes up in the validity of other researches. So we have something in special education called, well, we hopefully don't have it, but there was a methodology out there called facilitated communication, which essentially meant that with nonverbal students, a facilitator would put their hand on top of the hand of the student. And by doing this, the student was then able to use a keyboard and answer questions. And so this became a really popular thing because we've unlocked the magic of autism, and we can now get this student to make comments. Well, the problem was that there were a few cases where the facilitator said, do you want to live anymore? And the student then said no, and so then they actually killed the individual. And it's happened more than once, and we've had lots of things where these things have occurred. And the problem is that if you take that facilitator away, or if you could leave the hand on the hand, but if the facilitator doesn't know the question that's being asked to the student doesn't say anything. Only when the facilitator knows the question are they able to answer appropriately. So we see that it's the facilitator that is making those answers and not the student, and that's a big problem. So the state of practice in causal research and education. Theory and research suggest best methods for causal purposes, yet low prevalence of randomized experiments, low prevalence of regression discontinuity, low prevalence of interrupted time series designs. There's a low prevalence of studies combining control groups, pretests, and sophisticated matching. And we have a high prevalence of weak designs, pre-test, post-test only, non-equivalent control groups without a pre-test, and even with it. So there's a lot of bad research out there, and we're trying to improve that. Covariation is a measure of how much two random variables change together. Specifically, covariance measures the degree to which two variables are linearly associated. Validity is the approximate truth of an inference. It's a judgment about the extent to which relevant evidence supports the inference as being true. This is always entails fallible human judgment. It entails fallible tests. Evidence comes from both empirical findings and their consistency with past findings and theories. And so this is an idea about research and replication and our need to, just because one study said something, we need to be able to replicate that. This comes back to the idea of vaccines causing autism. Well, we know that vaccines don't cause autism. The study that was reported out there and that made all the news, and the guy went on press tours and did all these things, found an association between vaccines and autism. Well, the problem is that nobody was able to replicate his findings. So we saw this big thing, and other scientists said, wow, let's see if this is actually holding true. And they couldn't do it. And so the more it was replicated, the more it was found, this isn't true. We're not getting the same findings. And then it turns out the guy had falsified his data and everything was all a big mess. Validity judgments are never absolute. No certainty that inferences are true or that all possible alternatives have been falsified. What we don't want to say when we're writing a research paper or when we're writing up anything is that something has been proven. Results have suggested this. Results to date have concluded something, but we don't want to use really definitive terms like prove or we're sure or those kinds of things, because we're not sure. There could be studies that come out later that show that everything is different than that. Another example of this is the immunotherapies that we see for chemo or for cancer drugs on the internet right now, particularly Keytruda and Opdivo, are that they're really good for people with certain lung cancers, let's say. The problem is that some of these drugs, and I can't remember which one it was, but it was one that was being looked at under my treatment plan. Well, you have to have certain cell markers in it. So if you don't have the certain cell markers in it, it's not going to work. We wouldn't have known that had we not continued to replicate and find out under what circumstances these things work. The other thing that's interesting to note is that if you're east of the Mississippi and west of the Rockies, the likelihood of you having an allergic reaction to these drugs is like under 5%. However, if you're between the Mississippi and the Rockies, the likelihood of you having an allergic reaction is like 35%. So if all of our clinical trials were done just on the coasts, we would see less than 5%. But then you'd end up giving this treatment to people in between for whatever reason, and all these people would start having allergic reactions. And so it's important that we're replicating this research so that we can find under what conditions these things work and under what conditions they don't work. Validity is a property of inferences. It is not of designs or methods. Using a randomized experiment does not guarantee a valid causal inference. Validity could be broken by attrition, low statistical power, improper statistical analyses, and sampling error. Why is it important to remember that validity is a property of a knowledge claim, not a property of the design? Well, in the beginning, Campbell and Stanley, 1963, stated two different types of validity. There's internal validity, which is the inferences about whether the experimental treatments make a difference in this specific experimental instance. And then we have construct validity, which asks to what populations, settings, treatment variables, and measurement variables can this effect be generalized. So construct validity goes over here, and statistical conclusion and internal validity goes over here. To draw generalized causal inferences, it is useful to treat the causal and generalizability aspects of the inferences separately. So internal validity is one aspect, and construct or external validity is the other. So external validity means, can we generalize this to a larger population? And internal validity has to do with whether or not we had complete control over our experiment and there wasn't any other extraneous variables that were adding to that. And so it's a balancing act, because in order to get good internal validity, we have experiments that are very controlled. But to get good external validity, we have to have a large sample size and be able to, and a lot of different people, so that we would be able to generalize to those things. So it becomes a balancing act, especially in experimental research within the educational settings, where in order to have really good control over something, we would use something like a single case design where we would only have 3 people. But then we can't really generalize to a large population when we only have 3 people. We only generalize really to those 3 people and maybe a couple others that are exactly like them. And then to get good external validity, we need a whole lot of people, but in order to do that, we have barriers that are preventing us from controlling the experiment in the way that we would like to. Because a school system is nothing like a rat lab. So this corresponds to 4 questions. How large and reliable is covariation between the presumed cause and effect? Is the covariation causal, or would it have been obtained without the treatment? Which general constructs are involved in the units, persons, treatments, observations, and settings? They're using the term UTOS. I use the term PICOS, which is essentially the same thing: participants, intervention, control, outcome, settings. And how generalizable is the locally embedded causal relationship over UTOS? These questions and inferences are often considered separately, so it is practical to have the typology reflect that. However, they are often related and different combinations are possible, e.g. internal validity with or without construct validity. Consider the limits of combinations. For example, to what extent is both high internal and external validity possible, and what do we need for both? Well, what we need is the ability to control something and also have a big sample size. Threats to validity are specific reasons why we can be partly or completely wrong in our inferences about covariation, causation, constructs, or variations across UTOS. Heuristics, such as a list of potential threats, allow us to account for threats in the design or by including measures of anticipated threats. Sorry, I took a little break there. So, moving on to 3 critical questions about threats to validity. For any particular experiment and finding, how would the threat apply in this case? So when we're writing our research articles, or once we have our results, we want to discuss the limitations of the study, and that limitations of the study comes from the threats to internal validity, and we're going to explain those threats to internal validity and how likely they were, or how plausible is the rule. So we're not looking about possible, we're looking at plausible, which is a semantic distinction, but a very real distinction. Possible means, could it have happened? Sure, it could have happened. Is it plausible that it happened? Which means that is it realistic that it happened? No, because we controlled for it by doing this and this and this and this and this. Is there other evidence that the threat is plausible rather than just possible? Does the threat operate in the same direction as the observed effect so that it could partially or totally explain it? So, you're doing a study on anxiety, and in the middle of the study we have a huge earthquake or something, and so now everybody's anxious afterwards. Is that a plausible threat? Yes, that's a plausible threat. It's also a possible threat, and so we need to explain or account for the fact that this thing occurred. Ruling out threats is a falsification enterprise, so is always limited. The first threat that we're going to talk about is statistical conclusion validity. It is the validity of inferences about the covariation or correlation between the treatment and the outcome. How large and reliable is the covariation, whether the variables correlate or not, and how strongly they covariate. So this has to do with the statistical test that we employ, and this has to do with, we can p-hack, we can go through there, and we can try to find an association when there wasn't by controlling for all of these other variables and see if we can find something. And so we're interested in the statistical conclusions and the validity of those statistical conclusions. Then we have testing covariation. The null hypothesis. This is through null hypothesis significant testing. there's common misunderstandings of the p-value, and it tells us little about effect size. So the p-value, p, is the probability that this, whatever happened, is significant. And by significant, we mean that it didn't happen by chance. So p equals significance. And it is the significance that this thing didn't happen by chance. But all p really tells us is that whatever happened didn't happen by chance. It doesn't tell us, a really small p-value doesn't tell us that it was any more effective than a p-value that was right on the edge of our criteria. So p 0.05 is usually what we go with when we're doing statistical significance testing. That means that we have 95% confidence that whatever changes did not happen by chance. But a p of 0.01 doesn't tell us that that was better than the p05. All that matters is that it was below our significance testing, and that's it. So we don't know anything about how effective the intervention was. We just know that it did something. What about reporting effect sizes bound by confidence intervals instead? This is an alternative approach. It's recommended that these, along with the exact p of type 1 error, are related so that we would have a p-value, and then we would also have some sort of an effect size measurement. The CEC guidelines for evidence-based practices require both. Those guidelines, though, are for students with disabilities, so take that with caution. In the classic interpretation, exact type 1 probability levels tell us the probability that the results that were observed in the experiment could have been obtained by chance from a population in which the null hypothesis is true. Perhaps not the most interesting hypothesis. So we usually state, again, that p is less than 0.05. And if it is, then we say that our intervention was effective or whatever, so that we have met significance. But again, it doesn't tell us anything about the relationship of how effective whatever it was. An alternative interpretation of the p-value or the probability level signifies the confidence we can have in deciding among the following claims. Treatment A did better than treatment B, treatment B did better than treatment A, or the sign is uncertain and it's too close to call. Incorrect statistical conclusions, whether the variables covary. A type 1 error is a claim of a difference when there isn't one. A type 2 error concludes that there is no effect when in fact there is one. If I was to err on the conservative side, I would rather have a type 2 error than a type 1 error, because I would rather say that the thing doesn't work when it in fact does, than to say that there was a difference when there actually wasn't one. We're looking at how strongly they covary. If we overestimate the magnitude of covariation, or we can underestimate the magnitude of covariation. So threats to statistical conclusion validity. Low statistical power, which means that we have a small sample size. We don't have, small sample size is really the biggie. I mean, when we're looking at power analysis and we're looking at statistical power, the larger the sample, the more statistical power that we're going to have. The lower the sample, the smaller statistical power we're going to have. We violated assumptions of the tests, which meant that skewness and kurtosis might have been off. Fishing and the error rate problem, so we added a bunch of covariates and magically we got a p-value that was significant. We have unreliable measures. We have restriction of range and floor and ceiling effects, so if we only have a 3-question test and that test everybody gets it right, then we don't know whether or not a change happened or not. Unreliability of the treatment implementation. This would have to do with so the unreliability of treatment implementation has to do with why we put that part in there in the research report about treatment fidelity and how we measure it and how much it was implemented, because that's going to affect whether or not we can make some kind of a generalized causal inference. Extraneous variance in experimental settings, so we could have variance just due to students being in certain rooms. Heterogeneity of respondents, and that would be the participants, so they could be very different, which means that we could be throwing everything off because our sample was different, so different that we didn't get, or we did get findings from that. And inaccurate effect size estimation. Can we prove that covariation between a treatment and an outcome is zero? We can't prove anything. To support causal inferences, three things must be established. We need to make sure that A precedes B in time, which is the design of the experiment. That A covaries with B, which means that we use statistics to determine whether or not that there was any changes as a result of what we did, and that no other explanation for the relationship is plausible, and we use the design in that respect if possible. Then we focus on internal validity. It's the ability to infer with confidence that an independent variable has produced the observed differences in the dependent variable. We do that by isolating the independent variable, controlling confounds, and validity, again, is the approximate truth of an inference. Validity doesn't mean we prove anything. This is the approximate truth that, as far as we know, this is what it is. Validity of inference is about whether observed covariation between A, the treatment, and B, the outcome, reflects a causal relationship from A to B as those variables were manipulated or measured. Is the covariation causal, or would the same effect be obtained without treatment? We have local molar causal validity. Local is the generalizability is zero. It's limited to the units and the treatment and the outcome and the statistical, or I forget what S stands for now. Molar means the treatments are a complex package, and causal is restricted to claims that A caused B. One of the things that's most difficult to grasp about internal validity is that it is only relevant to the specific study in question. So the threats to internal validity are these. Each threat signifies a distinct class of extraneous other plausible causes. Ambiguous temporal precedents, selection bias, history, maturation, statistical regression, attrition, testing effects, instrumentation, and additive or interactive effects of these treatments. A way to remember this: his mother thought I started seeing different men. Sorry about that one. His would be history, mother equals maturation, thought equals testing, I equals instrumentation, started, statistical regression, seeing, selection, and different men, differential mortality. This is also attrition. So for history, this is controlled by isolating respondents from outside events. So that thing that I said about the earthquake coming in here, if we can control an earthquake happening, then we can control that from the outside. But we at least need to be able to be on the lookout for those historical events that might happen that could change our outcomes. And problems of history can be reduced by selecting groups from the same general location by ensuring that the schedule for testing is the same in both groups. So if both groups had the earthquake, we should be okay. We still might see a spike in the anxiety things, but if both groups had it, the historical threat is at least limited in some respect. Maturation, things like growing older, hungrier, or wiser if they could have impacted the score. So if we give a math test at the beginning of the year and then we give a math test at the end of the year, there would be maturation is likely to occur. They are likely to get better just as a course of the year going along. So we have to be able to control for that. And the way that we usually control for that is through a control group. This could come up with educational measures in general and also with intermittent depressive episodes. The person maybe get better over time, and that improvement may not have been due to treatment. We can reduce these problems by ensuring that all groups are the same age so that we know that they're going to mature at the same rate and and from the same location and perhaps other social groupings. Testing. Taking a test multiple times could impact improvement on that test without need for intervention. So if I give you the same test 4 times, you're probably going to get better on it, maybe, by the 4th time. So we usually vary the tests and have alternate form tests to be able to control for that. Some of the ways to reduce this are by creating different versions of the test that are calibrated to yield the same scores. This is done in curriculum-based measurement, where we will often have multiple versions of the probe. Instrumentation is any test or instruments will be upgraded over time. So if you're using a really old test, it may not work with the same reliability and validity as the newer test. It may be flawed in some way, so we need to be able to look at that. To reduce the problems of this, we need to make sure that we are using the same version each time. So you don't want to go from the Beck depression inventory number 1 and then use Beck depression inventory number 3 on the post-test. Another issue could be that the instrument was calibrated for a certain group and is being used on a different group. So if we calibrated this thing to work with white kids in Connecticut, it may not work as well for black kids in Alabama. Statistical regression. When extreme scores are selected, there's a tendency for them not to score so extremely on subsequent tests. Using a more reliable measure helps. Having a large sample of those extreme scores from which to draw from can help. And using standardized scores can also help. So what this essentially means is that if one day I scored way up here, but on subsequent administrations of the test I scored down here, this test doesn't accurately reflect what would have happened, generally speaking. So having a lot of people in there negates this possibility, because probably not everybody is going to have an extreme score. But those extreme scores, if we use them as the only method, can throw things off. Selection. The average person receiving treatment may differ from that receiving the control group. So we need to make sure that our treatment group and our control group are as equal on variables of concern as possible. Random assignment alleviates a lot of this problem. Attrition, also known as differential mortality. Participants in an experiment sometimes fail to complete the outcome measure. For example, drug therapy addicts with the worst prognosis tend to drop out of the study. So if you have somebody that's been addicted to heroin for the last 15 years and you have a bunch of them in the treatment group or in the control group, you're likely not going to see them again. And then we're going to have an inaccurate estimation of, so the people in the treatment group might stay with it, but the people not getting the treatment, and they're all heroin addicts, they might fall out and we might not be able to see them again. So we don't have an accurate picture of what the control group looks like anymore due to attrition, because the treatment group stayed in and the control group dropped out. In many cases, we will have guidelines as to how much attrition we will allow. You could use the internet to treat method of analysis or some variation thereof that will look at only analyzing study completers, or in the case of intent to treat, we take the whole sample beginning, and if they didn't complete the treatment, we consider that a fail. Threats to internal validity are not necessarily dependent of each other. Define two threats to internal no. Randomization controls most threats to internal validity, indeed all except for differential attrition and differential testing. Relating statistical and internal validity. Both concern operations, but not the constructs they represent. Statistical conclusion validity is concerned with errors in assessing covariation. Internal validity is concerned with errors in causal reasoning. Internal validity depends substantially on statistical conclusion validity. So if this doesn't happen, this doesn't happen. Evaluators often discuss external validity much less than internal validity. Some idea of disagreements in the field. Threats to validity often overlap. For example, attrition is listed as a threat to internal validity, but because sample size drops, it can threaten power, which is statistical conclusion validity, and may require changing how we describe who is and is not in the study, which is construct validity, and may raise questions about whether the intervention would have the same effect in those who dropped out. So now we move on to construct validity and external validity. Construct validity, making inferences about the sampling particulars of a study to the higher order constructs they represent. So a construct is a broad idea. So like reading ability is a construct. And so for example, we wanted to do a study investigating low socioeconomic status as a picture of education achievement. Our construct then looks at those receiving free and reduced lunch. What is the problem with this? Well, free and reduced lunch is generally the proxy that we use for socioeconomic status, but it doesn't necessarily mean that these kids are from low socioeconomic status. Whew. We are rarely concerned with just the measures that we look at as a proxy for the dependent variable. For example, the construct of depression is much larger than any of the scales that have been developed. Depression is a construct. We have developed scales to measure depression, but just because you don't meet the measures of those scales doesn't mean that you're not depressed, or vice versa. The importance of this is connecting procedures and experiment to a theory. Labels often carry social, political, and economic implications. So when we talk about treating students with emotional disturbances, well, that sounds bad, and so a lot of parents don't want their kids to be labeled with an emotional disturbance because it just sounds bad. And so a lot of times we will have students that meet the qualifications for an emotional disturbance, but they will be listed as something else. The creation and the defense of basic constructs is a fundamental task of all science, and we're really good at labeling people. This is fostered by starting with a clear explanation of the person, setting, treatment, and outcome constructs of interest, carefully selecting instances that match those constructs, assessing the match between instances to see if any slippage occurred, and revising construct descriptions accordingly. So we've had now 5 variations of the Diagnostic and Statistical Manual for the, now I've lost the part, DSM-4. We're on DSM-5 now. So the DSM-5 is a listing of constructs and how one might fit into one of these constructs. And so through revisions, we're now at DSM-5, and we now have a new set of mental disorders and the criteria for meeting those mental disorders. But if we use DSM-1, we might find different stuff. So we need to keep in mind that these constructs may have changed and that labels may have changed, and that those things may have changed. Developing and testing these constructs is one of the primary goals of structural equation modeling and other factor analyses. We need to emphasize operationalizing each construct several ways within and across studies. So if we're looking at depression, we probably want a couple of outcomes of depression, not just one. Probing the pattern match between the multivariate characteristics of instances and the characteristics of the target construct, and acknowledging legitimate debate over the quality given the socially constructed nature of both operations and constructs. The assessment of the sampling particulars of the study is essential for the weak and I don't even know what that's trying to say, so I'm going to delete that slide. Threats to construct validity are detailed on page 73, table 3.1. I'm going to delete that slide too. So for external validity, it is the extent to which external findings or a causal relationship that happened over variations in personal settings, treatments, and outcome. It is mainly concerned with generalization. If any original study, there was a demonstration of the phenomenon over a wide variety of conditions. In many cases, this requires getting a nationally representative sample, or at least a sample that we're describing in our study. So that's why when we're talking about the setting and the characteristics of the setting, we're being as explicit as possible, because this thing might have only worked in Manhattan, Kansas. We haven't tested it in an urban school. We haven't tested it on the West Coast. We haven't tested it on the East Coast. So we're only able to really generalize to Manhattan, Kansas. However, few researchers have thought things out well enough to determine all the conditions that may come up. Designing studies to anticipate all external validity questions may limit other design priorities like an internal validity. For example, questions of sample size. So if we got a nationally representative sample, we had 500 students in it, we're probably not going to have as much control over the experiment as we would if we had a small randomized control trial in Manhattan, Kansas. But then the generalizability of that small test or that small study in Manhattan, Kansas is going to be limited because it was only done in Manhattan, Kansas. So there's that trade-off. Threats to external validity. We have interaction of the relationship with units. We have the interaction of the relationship over treatment variations. We have interaction of the relationship with outcomes. No, I can't. No, it doesn't matter. Interaction of the relationship with settings, and the context-dependent mediation. So for interaction with units, an effect found with certain groups, an effect found with certain groups of people might not hold if other groups of people had been used. Interaction over treatment variations, perfect found with one treatment might not hold Effects found with one treatment might not hold with other variations of that treatment is combined with other treatments. So, for example, doubling up on an SSRI might have unintended consequences. In interaction with outcomes, a defect found that one kind of outcome observation may not hold if other outcome observations were used. For example, determining use of substances in a controlled treatment group would likely differ between using a self-report method and direct observation by the NSA. Interaction with settings. Effects found in one kind of setting may not hold if other settings are used. For example, though Corvallis, Oregon, and Manhattan, Kansas are similar in many ways, there are also many social differences that could confound the effects. And we have context-dependent mediation. The mediator of a causal relationship in one context may not mediate another. So we have random sampling, and this is random assignment can help greatly in improving many types of validity, particularly internal validity. However, many organizations are not going to be very receptive to it, and therefore external validity may suffer because you had to choose a different sampling method. Now we're going to move on to writing a precise research question, and this is going to be fairly short, and then we'll be done. So your research question should say something to the effect of, it should have listed in it the participants, the intervention, the control, the outcome, and the setting. This is almost the title of your study, just formed into a research question. So let's look at the research question that I did for the paper that I used when talking about the research. So let's go back to the research question. And for initial studies, it's probably better to just have one research question rather than a bunch of research questions. So my research question, to what extent is SRSD fractions, so this is the intervention, effective in teaching the addition and subtraction of fractions, this is the outcome, with unlike denominators to students with disabilities, and this is the participants. I didn't name the setting in here, but that's enough information. So we at least have 3 of those PICOs on there. That's what I'm wanting you guys to get to. So in your discussion question, after you've watched the other videos in this module, in the discussion, you're going to be writing the research question to the study that you will be proposing in 3 variations throughout this course. So try to get as many of these things. The control condition is probably not as necessary because we likely won't be establishing against a control unless we're doing something, unless our core. So I'm going to be doing a study where I'm hopefully going to be doing a study where I will be testing the partial products algorithm for long division versus the traditional algorithm for long division. And so my control condition could be that traditional algorithm. And in that case, I would put that in there because I would be saying something to the effect of, does the partial products or the partial quotients algorithm, is the partial quotients algorithm more effective than the traditional algorithm for students with disabilities? And then I would have the participants, the intervention, the control, the outcome, and the setting. But it may be that your control is just a business as usual type thing, and then we would start looking at maybe dropping that control from the research question. If you have any questions or concerns, give me an email, and I will get back to you as soon as possible.